everyone, welcome to my channel. So a while back, I was looking at my favorite YouTube channel, 3 Blue 1 Brown, and I saw this video on Fourier transform epicycle circles. I was like, wow, that looks pretty cool. I want to know how to make that for myself. So that's what this video is about. A quick Google search will show you hundreds of examples of simple line art. The issue is, these are all pictures with pixels. We have to find a way to make these into vectorized curves. My first thought was sweeping through the picture, going across the radius and marking down all the spots with a high black pixel concentration. The issue with this was that there was a lot of ambiguity in knowing whether to pick the furthest point or the closest point or something in between. I then tried coding up a sort of car that can see directly in front of it. It looks across all the angles it can see and picks the angle with the highest black pixel concentration. It then moves to that spot. This process repeats, hopefully moving across the curve. This seemed to work until it didn't. I tried changing up some parameters, but that didn't seem to work either. I thought maybe another image would work. I think this idea has a lot of potential. I'll be sure to visit it later. For now, I just resorted to manually clicking on the actual curve. To make sure that the point is at the pinpoint center of the curve though, I did check every pixel inside the click radius, making sure to place it at the very center of mass of the black pixels. This ended up working just fine, and you can see a couple of the resulting vectorized curves right here. I'm gonna go through this part pretty fast since there's a lot of excellent resources online explaining exactly how to do this. Starting with my favorite equation in math, Euler's identity. If we let t go from 0 to 2 pi, we see that the resulting complex number traces out a unit circle in the complex plane. Now if we multiply the complex number by 3, we see that the resulting circle is 3 times bigger. If instead we add a factor of 3 to the exponent, we see that the resulting circle is drawn at 3 times the rate. Now, if we shift t by a number such as pi, we see that the resulting circle starts at a different angle. What do you think happens if we add 2 of these numbers together? The real parts are added up and the complex parts are added up, vector style, and the resulting trajectory is just a little bit more complex. Pun intended. Interestingly, because addition is commutative, it doesn't matter if we add the smaller circle to the bigger circle or the bigger circle to the smaller circle. Both will make the same output. Now, say we add these somewhat random looking 7 numbers together. The output ends up being a square. Here's a zoomed in view showing all the little circles quickly coordinating with each other and figuring out the right angles. In the year 1822, the mathematical icon Joseph Fourier discovered that you can make essentially any function with enough of these circles. Before I show you how, I'm going to show you 2 little mathematical facts that will make everything else a lot easier. Say we multiply what we already have by a complex number c. C can be written in the Cartesian form as a plus bi, but we can also write it in the polar form as r e to the I theta. Now, in this form, we see that the theta can go up to the exponent and the r can scale everything. This way, with just one complex number, we have changed the magnitude and the phase of what we already had. Now, let's try integrating e to the int from 0 to 2 pi. If n is any number such as -2, 2, 10, 20, this integral will equal 0. This is because for any point along the circle, there will be a point on the other end of the circle that will exactly cancel this number out. So as we add all of them together, the integral will be 0. This rule is broken if n is equal to 0, because then it's not moving. Now, let's take an infinite sum of these complex forms, each at its own integer frequency, and each with its own complex constant. Let's set this equal to the function that we want. Now, if we just integrate this function, we see that all of those complex forms will cancel because of the rule we discussed earlier, except for one. This way, we can simply find out what the constant for the first term is. This time, before we integrate, let's multiply both the left-hand side and the right-hand side by e to the I times -1 times t. We see that on the left-hand side, because of exponential rules, this will shift all of the n's up by 1. So -3 becomes -4, -2 becomes -3, and so on. Now, if we integrate like before, we see that everything will cancel except for one of those, the one with the 0. This way, we can simply calculate another of the coefficients. By repeating this process, we can determine as many coefficients as we feel like. With this process, I was able to recreate this sketch of Shrek using 55 circles. With a small number of circles, the result will be very much an approximation. However, if we use a lot more circles, we see that the resulting curve is almost exactly the same as our input. For my final demo, I made a video in which the first frame is 1 circle, the second frame is 2 circles, the third frame is 3 circles, and so on. This looked something like this. Thank you so much for watching my first video. If you liked it, give it a like, and I hope to see you back here for more.